You might remember the mean value theorem for derivatives. The mean value theorem for derivatives said that if we had a continuous and differentiable function on an interval, on a closed interval, then there was a place at least one time in the interior of the interval where the instantaneous rate of change was equal to the average rate of change. Well, there's a very similar type of mean value theorem, but now it's for integration, for area. And this one says if f is a continuous function on the closed interval, we don't need the differentiability anymore, but we still need the continuity, then there exists a number c inside the interval such that the net area bounded by the function in the x-axis between x equals a and x equals b is equal to f of c times b minus a. Essentially what that's saying is there exists a single rectangle with area equal to the exact net area under the curve bounded by x equals a and x equals b. So in a picture, let's take a look. So here is my function, this kind of wavy piece right here. And what I'm ultimately trying to get at here is the net area bounded by that function in the x-axis between x equals a and x equals b. So I've got this region up here, I've got this region down here. And what the mean value theorem is suggesting is there is a place, kind of like how I've drawn in here, x equals c, and x equals c is the interior of the interval. And x equals c leads to the height of a single rectangle that is going to perfectly provide that exact same area as the net area underneath the function. You can kind of see that my rectangle does not include this extra area here, but it is picking up this extra area here. And so this is a really helpful tool in calculus, and you'll see as I get into some of the later examples, we actually use this all of the time for finding what's called the average value of the function. But this is an important theorem, and so let's practice it now. So it says, let's find the value of c guaranteed by the mean value theorem for integrals for the function being 9 over x cubed on the interval from 1 to 3. Okay, and so we can even take a look at what y equals 9 over x cubed looks like. So let's do that. Let's say 9 divided by x cubed. And let's go to the graph. Remember, we're just interested between 1 and 3. And so, so we're looking at this region in here, and what we're basically saying is there is a single place somewhere in that interval where we're going to be able to draw a rectangle, and that rectangle is going to have the exact same area as the total net area bounded by the function in the x-axis from 1 to 3. But we can just use the theorem. It's totally fine when it says apply the mean value theorem to simply plug into the formula. So this becomes the integral of 9 over x cubed going from 1 to 3 is equal to 3 minus 1 times f of c. And ultimately we're trying to get at c. So we're trying to get at the x value that we know has got to be somewhere between 1 and 3. That leads to this rectangle, and the rectangle again has the area here is the same as the net area bounded by my function in the x-axis from 1 to 3. So let's do the evaluation of this definite integral, and we can do this just using our ability to do antiderivatives and our new knowledge of the fundamental theorem of calculus. So that we have 9x to the negative 3 there. So I'd leave the 9, I would add 1 to that exponent, so that becomes x to the negative 2, and then I would divide by negative 2, and that's going to be evaluated from, so this is 9 over, I guess, negative 2x squared. That's going to be evaluated from 3 down to 1. And so that's going to give me 9 over negative 2 times 9. So that's just going to be negative 1/2 minus, let's see if I'm doing that right, negative 1/2 minus, now let's plug 1 in, 9 over negative 2. And so minus a negative 9/2. And negative 1/2 minus a negative 9/2 becomes negative 1/2 plus 9/2. That is 8/2, or 4. So the definite integral is equal to 4. And on this side, it's actually pretty easy looking. It's just 2 times f of c, which means f of c, the height of that rectangle, would be equal to 4 divided by 2, or 2. But I didn't want the height of that single rectangle. I wanted the x value in the interval from 1 to 3 that would produce that rectangle that would ultimately have the exact same area as the net area bounded by my function in the x-axis from 1 to 3. So if we want to know the c value when my y value is equal to 2, what we would do here to finish this question out is we would plug 2 in for y into the original problem. And then let's solve for x. So this would lead me to 2x cubed is equal to 9. X cubed is equal to 9 halves. X is equal to the cube root of 9 halves. And so if we looked at the cube root of 9 halves, the cube root of 9 halves is going to be somewhere between 1 and 3. Here, let's actually figure out what that is real quickly. I'm curious. So if we do 9 halves, which is 4.5, and we just say, let's raise that to the 1/3 power. That's doing a cube root. It's at 1.65. So if we go back to our graph, at 1.65, that's the x value that's going to lead to that one rectangle that you're going to be able to draw between 1 and 3, where the area of that rectangle would be the exact same as the net area bounded by my function in the x-axis from 1 to 3. And so you can imagine that this would simplify things in certain contexts. Now here's the most important takeaway from this. If you go back to this picture and we think about this one rectangle that produces the same area as underneath the curve between A and B, it's the height of the rectangle that is actually the average y value of the function on that interval. And if you think about it, I think you can make sense of it, because you see all of these y values, how they're offset by all of these y values that you have in here. And so the height of the rectangle, the f of c in this equation, is equal to the average y value of a function on an interval. So that's huge. That has really big implications. And so let's go down here and actually work with this now. So the average value of a function is f of c from above. And so when you get the question that says find the average value, you could simply say the average value is equal to 1 over b minus a times the definite integral of the function from a to b. And you could see if I multiplied this by b minus a, it gets me back to my original mean value theorem. So this average value of a function concept is a direct takeaway from the mean value theorem. So it's essentially doing the same thing, but here I guess I'm actually just isolating f of c, and I'm using this as my formula. So the average value of this function on this interval would be 1 over 4 minus 1, definite integral of 1 over 2x, going from 1 to 4. And so I'm going to take that constant out. So let's see, we have a 1/3, but then I'm also going to take that 1/2 out in front, and then I'm doing the definite integral from 1 to 4 of just 1 over x. And so this is going to lead me to 1/6 times, what is the antiderivative of 1 over x? Well, we know that is the ln of x. Let's plug in our upper limit, subtract what we get when we plug in the lower. And so we'll end up with 1/6 times the natural log of 4 minus 1/6 times the natural log of 1. But what is the natural log of 1? A lot of you know that that's equal to 0. So this term kind of gets wiped out. So this ends up being our answer. So this is the average y value, of this function on this interval. Okay, let's do one more. Let's find the average y value of cosine of x on the interval 0 to pi over 2. And so we would say the average y value is equal to 1 over b minus a times the definite integral of our function from 0 to pi over 2. And so 1 over pi over 2 is equal to 2 over pi. And then the antiderivative of cosine is sine. Let me plug in my upper limit, subtract what I get when I plug in my lower limit. So this gives me 2 over pi times the sine of pi over 2 minus the sine of 0. The sine of pi over 2 is 1, and the sine of 0 is 0. So this actually just ends up giving us, since this is just 1 and this is 0, gives us an average y value of 2 divided by pi. Okay? Sometimes in WebAssign, what they will ask you for is, they might say find the average value of the function, but also find the x value that has that particular average y value. So these answers might not suffice. If you needed to find the x value that leads to this average y value, it's kind of like what we did back in example 6. What you want to do is you want to take this and substitute this in for y into your original function. So like here, if I wanted to know the x value that leads to my average y value of 2 over pi, I set 2 over pi equal to cosine of x, and then I could solve for x. Or here, I would set 1 over 6 times ln of 4 equal to 1 over 2x, and again, solve for x. Okay, next video, we'll look at what's known as the second fundamental theorem of calculus, and you should check that one out now.